everyone, my name is Christine Park and this is my lab report for Lab 1, Constant Velocity. So just to give a brief introduction of what the objective of this lab was, in this lab I used footage of an object moving at a constant velocity and put this footage into the tracker software to manually analyze the change of the object's position over time. I then used some key findings in this experiment to create a computer-generated model with predictive data. The main physics principle that was addressed in this lab was Newton's second law, which can be demonstrated by acceleration equals net force over mass, or final velocity equals initial velocity plus net force over mass times change in time. Both of these demonstrates that acceleration depends on the net force and the mass of the object in motion. In this case, velocity is constant, which indicates that there is no acceleration. And using these equations, we can see that the net force is equal to 0 and the mass is constant, so the acceleration must equal 0. So here is the video of my experimental model. Just a few variables to begin. The mass, I chose to roll a mini tennis ball with a mass of 0.15 kilograms with a diameter of 0.044 meters. So I'll play the video now. So these were some of my key findings from this experimental data. So we knew what the mass was and we knew what the observed start time was, as well as the diameter. But some of the new findings that I found through this experiment was the initial position vector, which was negative 0.252, comma, negative 0.01733, comma, 0. The initial velocity, which was 0.45, comma, 0.004, comma, 0, as well as the observed end time, which was 1.068 seconds. I then used these findings to alter the sample code in GlowScript. So I made some changes. So the first one being the mass to 0.15, the initial position vector, which was negative 0.252, comma, negative 0.01733, comma, 0. The initial velocity, which is 0.45, comma, 0.004, comma, 0. The observed start time, which was 0. The time step, which was 0.01, as well as the observed end time, 1.068 seconds, and these were my results. So using the data from both the computational model as well as the experimental model in Tracker, I created this line graph displaying both sets of data. So as you can see, for the model data in red, it's a straight line with a consistent slope all the way through. And in the experimental data, you can see how it starts off pretty straight and consistent, but then it starts to become more inconsistent with a decrease in velocity, and this can be due to various human errors, one being the inconsistency when it came to mapping the center of mass of the object between frames in Tracker. Another could be how the ball didn't roll in a straight line on the countertop, which visually distorted the footage. And then lastly, there could have been a change in velocity that I did not catch and I did not cut out. And then going into the what-if questions. So what if the x-axis was flipped? So positive would be negative, negative would be positive. The orientation, if the orientation was switched. The values would stay the same, but the order in which they would be plotted would be switched. So the graph would have a negative slope and appear to be decreasing from left to right as time would be moving from greater to lesser as you move from left to right. And then what if the x and y axes were switched? If these axes were switched, the slope would be much steeper. This means that the graph would be plotted as time over position rather than position over time, where slope would equal change in time over change in position, or t over s, or 1 over velocity. And then finally, so what does it mean? How many pushes and pulls are added together to create a net force of 0? So referring to the formula that I referenced earlier, where force equals mass times acceleration, we know that there's no force being applied in the x direction, and we can use this formula to prove it. Since there's no acceleration, F would equal mass times 0, which means that the net force is equal to 0. However, in the y direction, there are forces at play. There's a gravitational force on the object moving in the negative y direction, pushing down on the object at 9.81 meters. And then there's an equal force being exerted in the opposite direction, which is called the normal force. These forces would cancel out and create a net force of 0.